Hello everyone, I am Sidhartha from Indraprastha Institute of Information Technology, Delhi, India. In this presentation, I will discuss on my PhD work, that is efficient post-silicon debug platforms for future mini-core systems. Modern day system integrates multiple processing cores on a single chip. Network on chip is popularly accepted as the scalable interconnect medium for such many-core systems. With the growing complexity of the systems, most of the state-of-the-art NOCs are becoming extremely complex in their design. To validate such complex NOCs, traditionally trace-based post-silicon debug methodologies are adopted, where DFD structures are integrated to NOC-based systems that facilitate trace collection, trace storage, trace transfer, and trace analysis for the validation of the NOC. In this context, three different issues with existing debug platform are highlighted. First one is bandwidth limitation, which refers to the low bandwidth JTAG interface for off-chip trace transfer to the debug analyzer, leading to a longer debug phase. Second one is trace buffer size that directly translates to the area and power overhead of the debug structure. Third one is debug hardware is unused once the debug phase is over and is considered vestigial after the mass production. My PhD work proposes three different solutions corresponding to the three discussed issues. The first solution is WIND, that is wireless enabled debug platform, where high-speed wireless interfaces are augmented to the NOC debug structure for both off-chip trace transfer and network trace reduction. The second solution is RTE, that is a mechanism to eliminate redundant traces for trace size reduction. And the third solution is redesign, that is reuse of debug hardware for system performance enhancement during in-field operation. Let us start with the first solution. In a wired NOC, the packet communication is performed through router path. An example packet communication from node 26 to 11 for XY routing can be realized as shown here, where the packet traverses across 7 router nodes to reach its destination. However, in case of a wireless enabled NOC, the packet takes the wireless path and traverses through only 2 router nodes to reach its destination. This shows that the average life of payload packets reduces considerably in case of a wireless enabled NOC. Our proposed debug framework divides the NOC into few clusters and integrates one wireless interface per cluster of the NOC. These WIs allow on-chip test payload wireless communication for long-range test packets, leading to reduced average life of these packets. As a result, the framework achieves considerable trace reduction, which allows more frequent trace collection for a fixed size trace buffer, and availability of more traces enhances fault detection and localization. Our framework uses a portion of local cache of each node as local trace buffer, which are released for normal operation after the debug phase. Packet traces at each node are collected in a periodic manner and are stored in its local trace buffer. Once any of the local trace buffer gets filled up, the traces from all the nodes are transferred to the WI of the corresponding cluster using the wired NOC path. Such reuse of NOC infrastructure for on-chip trace transfer eliminates the requirement of on-chip trace bus, and provision of wireless interface in each cluster provides regional output interface. The collected traces at each wireless interface take the wireless path to the off-chip external debug analyzer. Thus, the framework provides high-speed inter-chip wireless transfer. To achieve the best out of our proposed framework with minimal overhead, it is important to find out optimal number of WIs and optimal placement of WIs. The optimal number of WIs depends on two metrics such as less trace generation and cost of the DFD structure. An aggregate objective function is developed using these two metrics. A simulated annealing-based optimization process is adapted to find the optimal number of WIs that achieves the minimum AOF value. Moreover, WIs are optimally placed within the clusters so that they can be at close proximity to the busy nodes of the cluster. This allows busy nodes to evacuate their traces quickly. In this case, the driving metric is total shortest path in cluster between each node of the cluster and the WI. WIND provides up to 16 Gbps off-chip trace transfer speed, which is much higher than the traditional JTAG-based trace communication. The framework also provides 30% improvement in fault detection and path reconstruction. Let us discuss our second proposal, that is redundant trace elimination. NOC is a shared interconnect medium. With increased network traffic, network congestion increases, which results in increased packet waiting time in the intermediate routers on the packet traversal path. During the waiting period, there is no change in the packet state, therefore the traces collected during this period are redundant. Our proposed redundant trace elimination framework provides the infrastructure that can detect and eliminate the redundant traces. The trigger unit periodically generates the trigger signal for trace collection. The packet monitor unit continuously observes all the packet states inside the router node and captures and forms the packet traces as soon as there is a trigger signal. The newly formed trace is examined in the RTE unit that whether it is a redundant trace or unique trace. If found redundant, the trace is eliminated. Otherwise, the unique trace is transferred to be stored in the trace buffer. This figure shows the circuit diagram of the proposed redundant trace elimination unit. Our simulation result shows that the percentage fault detection and path reconstruction increases when traces are collected for smaller interval, and the proposed RT scheme achieves maximum trace reduction for this case as shown in figure A and B respectively. Similarly, figure C and D shows that RT mechanism reduces maximum traces in case of deadlock fault and at saturated PI respectively, which are the cases that generate large amount of traces otherwise. RT scheme provides up to 36% trace reduction. Let's discuss our final solution, that is reuse of debug structure. Debug structure becomes vestigial once the debug phase is over and remains unused on the final silicon chip during the in-field operation. So reuse of debug structure for architectural purpose compensates the area overhead incurred by it. Our solution proposes to reuse the trace buffer as extended virtual channel of NOC routers for system throughput improvement, trace prioritization hardware for critical data prioritization, and packet monitor module along with trigger and timestamp unit for packet starvation control. Figure A shows trace buffer used for storing packet traces during debug mode, and figure B shows that the local trace buffer is used as extended VCs of the router node. Availability of more VCs allows storage of more payload packets during in-field operation. This enhances the system performance as the packet drop considerably reduces. For trace buffer distribution, offline profiling of all router nodes are performed based on all the applications mapped onto the NOC. Then a profile index and accordingly a value function is calculated for each of the router nodes. A trace buffer share is provided to each of the nodes according to its value function using a modified fair division algorithm. This provides an optimal distribution of trace buffer so that busy nodes get larger portion of it to store more traces during debug and to store more payload during normal execution. Redesign framework divides the whole network into few clusters and provides an interface to trace bus from each cluster known as network trace port. During debug phase, whenever there is a trace buffer overflow, the traces of the field trace buffer is transferred to the cluster's NTP with high priority. Trace priority hardware is implemented in the arbiter circuit of the VC allocator. During trace transfer, only except the router nodes on the trace travel path, all other network nodes continue with normal operation. This provides improved debug speed due to less interruption in normal operation and relatively less local trace buffer overflow achieved from optimal trace buffer distribution. Moreover, during in-field operation, redesign framework achieves high network throughput because of more VCs available at each input port of every router. Prioritization of critical data such as main memory access packet can provide faster movement of such packets on the network and thereby can improve the system performance considerably. Redesign framework reuses the trace prioritization hardware for this purpose. With network congestion and stringent prioritization protocols, many data packets with lower priority suffers from resource starvation and thereby not able to move forward on the network. In our proposed framework, packet monitor unit of the debug structure is reutilized to observe the waiting cycles of each packet inside a router and provides a temporary critical status to starved packets for their forward movement. The proposed redesign framework increases network throughput by 11% and decreases average network delay by 14% during in-field operation. Moreover, it provides 18% decrease in critical data latency and 7% decrease in packet starvation. This table shows the simulation setup used to generate results for the proposed WIND, RT, and redesign platforms. In conclusion, my PhD research work proposes three post-silicon debug solutions, namely WIND, RT, and redesign. WIND provides high-speed trace transfer, RT reduces the trace amount, and redesign reuses the debug structure for system performance improvement. As a whole, my PhD thesis leads to development of an efficient and low-cost post-silicon debug platform for NOC-based MPSoC systems that can be reused for system performance enhancement during in-field operation. This is the list of publications out of my PhD work. Thank you very much for paying attention to my presentation.